Hello, class. Hello, everyone from Hawaii. Oh, no, just kidding. That's the Zoom's function. You can set the background as a beach like this. Actually, I'm still in Taiwan. So today we are going to talk about chapter number 6, a series of a higher order ODE. Let me turn on my PDF of the textbook. Uh, as I already posted on island of this PDF, you can watch the PDF of our textbook, and basically it's the same as your paper version, but this is an older edition, so maybe a little bit slightly different from your paper versions. Okay, so chapter 6, theory of a higher order linear differential equation. Basically, chapter is an extension of chapter 4. Uh, mathematicians like to generalize everything. So chapter 4, we only talk about second orders linear differential equation. Here, we want to generalize to nth order linear differential equations. So you can think of the chapter 4 is a special case of chapter 6. So everything is almost the same as chapter 4, just more general, that's all. So let's start from section 6.1, basic theory of linear differential equation. Linear differential equation of order n. Let me turn on my tools. Okay, I think I need some tools. Yes, I need some drawing tool. Okay, okay, good. So basically, a linear differential equation of order n is an equation that can be written in the following form. So this is the general form. This is the general form of nth order linear differential equation. As you can see, the highest order of derivative is nth order here. And the anx, an minus 1x, dot, 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 to a0x are coefficients of these ODEs. They are only dependent on x. They cannot depend on y. Once these coefficients depend on y, that will be nonlinear. They won't be linear. For example, if a0x is y, that will have y squared, then this will be a nonlinear equation. Same as before, you can see the right-hand side, we have a bx. If bx is 0, then we say as before, we call it homogeneous. Otherwise, if bx is a non-zero function, we also call it as before non-homogeneous. In Chinese, homogeneous is 均匀, non-homogeneous is 非均匀. Usually, we want to make sure this coefficient a0x, a1x, dot, 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 anx, and the bx are continuous on an interval I, especially for the leading coefficient anx, they cannot be 0 on I. If there are some point on I such that anx is equal to 0, then this will vanish. That means it won't be nth order equation. So we request anx won't be equal to 0 for any point on I. Usually, if you make sure anx won't be 0 for any point on I, we can divide the whole equation 1 by anx, and it becomes the standard form called as equation number 2. So you can see the leading coefficient of the highest order term, ynx, will be 1 here. And the other will be the P1x will be just an minus 1x divided by anx. And so on. A0x will be just become Pnx, which is A0x divided by Anx. And the same Bx will be the Gx will be Bx divided by Anx. And we request the P1x, Pnx, and the Gx are continuous on I. Okay, so the next, let me erase this. Let me erase this. Okay. So, first theorem we are going to study is theorem 1. It's about, same as before, it's about the existence and uniqueness of an initial value problem. It's very easy. So it's just like the previous one, just extend it to nth order equation. Okay, so suppose P1x, Pnx, and the Gx are continuous on some interval AB that contain the point x0. For any choice of initial value, gamma 0, gamma 1, to gamma n minus 1, there exists a unique solution on the whole interval AB to the initial value problems. So equation number 3 is our equations, ODE, and equation number 4 just is our initial condition. Remember, as we said before in chapter 4, we want to solve this equation. So that means we need to do the integration. Here, the highest order is nth derivative. So we need to integrate n times to find the solution y. When you're doing the integration for n times, it will generate n integration constant. How can you determine n integration constants? You need to have n equation for that. That means you need to have n initial condition for that. So here there is initial condition. As we say, the initial condition must start from the lowest order. So the lowest order is y itself, y x0 equal to gamma 0, y prime x0 equal to gamma 1, till y n minus 1 x0 equal to gamma n minus 1. You can count. There are n initial conditions. So you can determine n integration constant. Okay, let's move to example number 1. For the initial value problem, we have number 5, and this is equation, and the number 6 is initial conditions. Okay, so the question asks, determine the value of x0 and the interval AB containing x0 for which theorem 1 guarantee the existence of a unique solution on AB. Okay, so by theorem 1, you need to make the leading coefficient to be 1. So here we are going to divide the whole equation by x times x minus 1. That means you will get P1x equal to minus 3 divided by x times x minus 1. Let me use the laser point. So P1x is here. P1x is here. P2x is 6x squared divided by x times x minus 1. So become 6x divided by x minus 1. The same, P3x will be minus cosine x divided by x times x minus 1. The same, Gx will be square root of x plus 5 divided by x times x minus 1 here. And we need to make sure P1x, P2x, P3x, and the Gx must be continuous on some interval. And this interval must contain x equal 1 because x equal 1, sorry, this interval, as we can see, this interval cannot contain x equal 1 because that will make the denominator equal to 0. Okay, so the same, you cannot have this interval contains x equals 0 because you will make the P3x, the denominator in P3x equal to 0 again. So the function gx here also, again, we have the square root of 5. You need to make sure the square root or inside the square root, it must be larger than or equal to 0. So x can only less than -5. Okay, okay. So the function gx is not defined for x minus 5. Also cannot be defined on x equal to 0 and x equal to 1 because it will make the denominator in gx equal to 0. Okay, so it seems gx is the dominant one. So gx is only continuous -5 to 0, 0 to 1, or 1 to infinity. Okay, and function p1, p2, p3, and g are simultaneously continuous only on interval -5 to 0, 0 to 1, and 1 to infinity. Okay, so from 0 and 1, we can only choose one of these three intervals. For example, if your x0 is located between -5 and 0, then you need to choose the interval should be -5 to 0. Otherwise, if your x0 belong to between 0 and 1 interval, then you should choose your interval should be interval 0, 1. Okay, the same if your x0 is located in 1 to infinity, then you should choose this infinity, 1 to infinity, this interval. Okay. Okay, so the next one, we are going to talk about some important notations called differential operator. Let me activate the pen. Okay, let me, okay. This is important. Differential operator. In this chapter, we are going to talk about differential operator very, very often. Okay, so all of you need to memorize its definition. What is a differential operator? In Chinese, it's called 微分运算元，或者是微分运算子。Okay, so here is the definition. We have a differential operator L working on some function y. 但是 L working on y function means is dny over dxn plus p1 dn minus 1 dy dxn minus 1 plus dot 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 plus pny. This is exactly the left-hand side of our ODE here, right? Remember, huh? This is exactly. So you can think of differential operator means working on y means it will form the left-hand side. It will form the left-hand side. Let me activate the pen. It will form the left-hand side of our ODE here. Okay. Okay. So that is the definition of a differential operator. Okay. And sometimes we don't like to to write this Leibniz notation because it's very it involves many words. So remember, we use capital D to represent d over dx. So here we are just going to use this simple notation, capital D. Remember, D. Let me write down. In your when you learn calculus, you must know this. Let me activate the pen again. So in calculus, you will learn this is Leibniz notation, right? D over dx is Leibniz notation. Now you can write it as D. So, for example, the derivative of dy over dx equal to d over dxy further equal dy. Oops, sorry. I didn't. Hold on. Sorry. Let me use erase. Okay, so again, let me see. In calculus, we will learn dy over dx. Oh, I forgot d. Oh, and this pen is not very handy. Let me. We will learn dy over dx equal d over dxy equal capital dy. So d here is actually d over dx. Okay, so let me erase this. So we are going to use this. This is very important. We are going to use this this form a lot. So this is important. We are going to use this a lot. Okay. Okay. So in short, we can write equation 7 in short, just like equation 3. Sorry, equation 3. So equation 3 is our ODE. Remember, it's standard form of our ODE. So in short, we can use a differential operator to write our equation 3. Our equation 3 simply like L y x equal to gx. Sometimes I even just write ly equal gx. Sometimes, so let me write it down. So sometimes I just write. Let me activate the pen. So sometimes I will just write as ly equal g. That will be the simplest form. Okay. Okay. Let me erase this. Okay. Remember, the form here is this differential operator is linear. What does it mean linear? The linear always need to satisfy the following two property. Property 9 and the property 10. That means if L work on the sum of the following sum: y1 plus y2 plus dot 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 plus till ym will be equal to L working on individual y, then sum them up. The same, if L work on cy, it will always, this constant c can be moved out of this the bracket, becomes c times ly. This is two property define linearity. Linearity. Okay. So remember, in this chapter, we are going to learn the nth orders linear differential equation that will be represented by equation number 8. As before, in chapter 4, we always start from the homogeneous equation. That means gx equal to 0. So here the same, let's start from the homogeneous equation, Lyx equal to 0. Okay, so assume y1, y2, dot, 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 ym are all solutions to the homogeneous equation. Then any linear combination of this function, that means they are, it is c1 y1 plus c2 y2 plus dot, 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 plus cm ym. This is called linear combination of this function, 线性组合. As we know from linearity, it is also a solution. This can be proved very easily. You just apply L on this linear combination, and by the linearity property 9 and 10, it can be equal to C1. You can get a C1 outside the bracket times Ly1. And since y1 is the solution of the homogeneous equation, so Ly1 becomes 0. The same for the C2 y2 term, you got C2 times 0, and so on. The last one, Cm ym, it will be equal to Cm times 0 and equal to 0. Okay, so now if we can find n solution, y1, y2, dot, 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 yn, to nth order linear equation, is it true that every solution to our homogeneous equation, 11, can be represented by the linear combination of these n solutions? Well, that is equivalent to say, if this linear combination of this n solution is the general solution of our homogeneous equation. Okay? Okay, so let's stop here, and I will see you again soon.